So how do we find the gravitational potential energy? We all familiar with this concept of finding the potential energy of an object at a height h from the Earth's surface, and particularly if the height is not that big. So this is Earth's surface, and we have a mass m from the Earth's surface at a height h, and there's another mass here which is at a height of 2h. So how do we calculate the potential energy? So in this case, we say it's mgh, and here because it's 2h, it's 2 mgh. So potential energy is about the work done by moving an object to a distance. So we multiply the force and distance, and that's the potential energy gained by the object. So in this case, mg is the force, h is the distance. Here, mg is the force, and 2h is the distance, so it's 2 mgh. But we're making an assumption here that g is constant. We use 9.8 for the gravitational acceleration when an object is very close to the Earth's surface. But if the distance, in this case, if we say 38,000 kilometer, we won't be able to use g because we know from the previous videos we found out that the g changes. If it's g here, it might be g1 here, g2 here, g3 here. And we derived an equation for the gravitational strength, which is g is equal to gm over r squared. The mass is m is the mass of the planet, r is the radius of the object from the center of the planet, and g is the universal gravitational constant. So to find the potential energy of an object at a distance r from the center of the planet, we can use this formula for g. So gravitational potential U is equal to m. Instead of g, we're going to put gm over r squared times r. So we will get g m m over r. So that's the equation for gravitational potential energy. But there's something else we need to understand here is we always put a minus here. So we're using a minus value for the gravitational potential energy here. If we have a mass at distance r, where we have the potential energy UR is equal to minus gm m over r. When we talk about distances like very low values from the Earth's surface, we always assume that the potential energy at the Earth's surface is zero. So it's zero here. So that means that potential energy at this point is mgh. Potential energy is the work done to lift an object from here to here. But when we talk about distances, massive distances like planetary scale, where we're talking about 40,000, 30,000 kilometers, we consider that the potential energy at infinity is zero. So if it's zero here, the UR, that means the potential energy in, if this is A, this is B, at point A must be less than U infinity. So UR must be less than U infinity. Why? Look at a point here. If this is X, this is Y, what we know from here is that UY is greater than UX. UY is greater than UX because as we lift the object higher, it its potential energy increases. In the same way, if we take the object further from the planet, the potential energy increases. But if we consider the potential energy as zero at this point, we know that at this point, this is less than that one. That means UR is going to be a negative value. So we can write down UR must be negative. Why? Because U infinity is 0 and UR is less than U infinity, so it must be negative. If I take a planet here and there are two orbits, one is here, one is here, and this is orbit X, orbit Y. So let me put some values for the potential energy at X and Y. Mass M minus 30. So if it's minus 30, can you tell me the potential energy in Y? All that we know is that potential energy at a greater height compared to this one, it must be bigger. So we were talking about something like minus 20. But if you look at only the magnitude, you can see the magnitude at X is bigger than 20 because 30 is bigger than 20. But if you look at the sign, minus 20 is bigger than minus 30. So we need to be very, very careful because we use the negative value for the potential energy. At the same time, we also know that as the distance from the center increases, the potential energy of the object will increase. So if you look at only the magnitude, it will be less than that. But if you look at the sign, it will be greater than that. But what is going to happen is that as it increases, at a point it comes, the potential energy will be zero. That's what we considered as infinity because it will keep increasing up to a point where it will become zero. And so another last point to look at is that the potential energy at different points. So looking at this, we can see that as the radius reaches infinity, that potential energy is becoming zero, but at Earth's surface, it's negative. So what does that say? So that means that the value at infinity, or here, it's greater than the potential energy on Earth's surface. So that because this is a minus value and this is zero, so zero is greater than the minus value.
There's another way to look at this is because we said that it's zero here, close to Earth, so it's a positive value because this is the work done to lift the object to this place from zero to here. So that's plus positive mgh. But when we have a reference point here as zero at infinity, so the potential energy is work done to bring the object from infinity to point A, where the radius is r. So in this case, we are doing the work to lift the object, but in this case, the work is done by gravity. So we are not doing the work, gravity is doing the work. So that means the work is minus. So that's another way to look at why the potential energy is minus.
So this is a question on gravitational potential energy. We have Earth and a satellite A, and satellites, when they go on orbits for some time, particularly the ones that are the near Earth orbits, at a distance, say 300 kilometer, 400 kilometer, they are closer to the Earth. What happens is that eventually they lose the total energy due to the atmosphere, Earth atmosphere, and and when they lose energy, they fall into low orbit. So from A to B. So in this question, it was 300 kilometer and it's come to 290 kilometer. It's falling to this orbit, and we are asked to find what is the change in potential energy. So previously we found out that the potential energy at A is greater than B because it's a high orbit, it's a low orbit. And the data given to us is altitude. That's another thing we need to be very careful. Altitude is a distance from the surface of the Earth to the point where the satellite is. So we have to add the radius of Earth to find the total radius or the total distance from the center of Earth to the satellite. So when we have an equation gmm over RA, that RA is the total distance. That's the Earth's radius plus the altitude. So this is given to us, the Earth radius, which is 6.37 plus 10 to the power 6 meter. It's always given the data sheet. And the mass of the Earth is given here. And we know the mass of the satellite in 75 kilogram. So we have the radius and everything in meters, mass in kilogram. So what we need to find out is that we need to find the gravitational potential energy at A and at B, and we find the difference. So the difference will be whether it will be plus or minus. It'll be minus because the gravitational energy is going to be reduced when it falls from A to B. So this is the final and this is the initial. So let's start to write the equation for the difference. So if we say that delta U is the difference between UB minus UA. So UB is gmm over RB, this is a minus here, UA is equal to minus gmm over RA. So what we have here is UB, which is minus gmm over RB, minus, well, that would be plus, because we have a minus here and then minus, so gmm over RA. So if you look at this radius here, RB is less than RA. So from here, because we are dividing this fraction, we're dividing that by RP is less than RA. So we're going to have a bigger minus value and smaller plus value. So the answer is going to be minus. That clearly shows that the gravitational potential energy is going to be reduced. So let's substitute all the values that we have got. We have got the value for RB, that is radius of Earth plus the altitude of B, and this one radius of Earth plus altitude at A. So if we substitute those values, so if you substitute all the values correctly, you will get an answer delta U, the change in gravitational potential energy, will be minus 6.72 megajoule. So So we have got all the values here. We got the mass, the small mass, the mass of the satellite. We got the mass of the Earth, and we got the value for G. So all that we need to do is we just substitute those values, and we will get 6.72 megajoules as the change in gravitational potential energy.